In the following video lecture, we're going to compare the primary halogenoalkane reaction mechanism, which is the Sn2 mechanism, with the tertiary halogenoalkane reaction mechanism, which is the Sn1 mechanism, and we're going to figure out what would happen with the secondary halogenoalkane. So first, I'm going to go through the primary halogenoalkane reaction mechanism for nucleophilic substitution. So remember that a primary halogenoalkane was a carbon that was bonded to Cl, but that particular carbon atom, this alpha carbon atom, was bonded to two hydrogens, at least two hydrogens. There could be three hydrogens as well, and on one side there was a carbon chain. Now the reason why this nucleophile, and I picked the OH-1 nucleophile, the reason why this OH-1 nucleophile is able to approach this positive carbon atom, remember this bond over here is polarized because Cl is highly electronegative. So Cl has a slight negative charge and carbon has a slight positive charge. And this OH-1 nucleophile because it's negative, it has extra electrons, it's going to be attracted to this positive carbon atom over here. The reason why this OH-1 nucleophile is able to approach this positive carbon atom is because around this carbon atom, if you look around this carbon atom, there are two very small atoms of hydrogen. Hydrogen doesn't take a lot of space. So there's a room for attack from the backside. So this OH-1 can sneak up to this carbon atom and its electrons can be attracted to this positive carbon atom. And as it does that, the electrons in this Cl bond over here, they are going to get repelled. So these electrons over here, they would be repelled, and slowly this OH would approach and this Cl, the electrons in this bond would get repelled. So this is the second step of the reaction. The second state, this is called a transition state. The OH is slowly approaching this positive carbon atom, so its bond with this carbon atom, its force of attraction with this carbon atom is getting stronger, and Cl is taking away those electrons and is getting repelled, and in the next step the Cl-1 is knocked out and the OH nucleophile is able to take its position. So the main reason that I'm trying to highlight is that this carbon atom has a lot of room around it, so this OH-1 nucleophile can attack from the backside. Now in the case of tertiary halogenoalkanes, if you look at this tertiary halogenoalkane, a tertiary halogenoalkane is that the carbon atom, this alpha carbon atom that is bonded to chlorine, the halogen, would be surrounded by carbon chains. So on all three sides there would be large groups or carbon chains attached around it. Now carbon and along with the hydrogens, if takes a lot of space. So the problem would be that if I draw an OH, and again this bond is polarized, carbon has a slight positive charge and Cl has a slight negative charge because of the high electronegativity of the chlorine atom, so the electrons would be closer to chlorine. Now the reason why the OH-1 nucleophile cannot approach this central carbon atom in this case is because on all sides large group of large structures like the CH3 structure, CH3, on all sides there are carbon chains. So this OH-1 cannot approach this carbon atom. There's no possibility or room for attack from the opposite side. So and plus because of the alkyl chains, there are lots of electrons. So the positive charge density of this carbon atom would decrease because this positive charge is going to attract electrons from these carbon chains, and the positive charge is going to be less dense, or it would be slightly neutralized by the carbon chains, alkyl chains around it. So this OH-1 has no room for attack. So initially it's not going to attack this carbon atom. There's no possibility of an attack. There's no space available. And plus the positive charge is not strong enough, so this OH-1 is not attracted initially. So in the first step, the OH-1 has nothing to do. So what happens is that during collisions, you heat up the mixture. There are chances that the Cl atom is knocked out on its own. If it gets knocked out, then there's a possibility, because Cl takes away electrons and this carbon loses electrons, and this carbocation intermediate is formed, and this carbon is going to have a positive charge. Now there's room available for an attack, and this OH-1 would quickly get attracted to this positive carbon atom and it's going to join with it. So the reason why an Sn2 mechanism is not possible with a tertiary halogenoalkane is that there is initially no room for attack by a nucleophile. It cannot reach this positive carbon atom, and this force of attraction is not strong enough. So the first step in this case is different. For tertiary halogenoalkanes, the first step is different. The Cl gets knocked out on its own, and when it gets knocked out, a carbon loses its electron because Cl is going to, if the bond breaks, it's going to be a heterolytic bond fission, and the Cl ion is going to take away the electrons in the bond because it's highly electronegative. So carbon has a positive charge, and in this next step, this OH minus 1 would be able to fit in. Now we're going to discuss what would happen with secondary halogenoalkanes. I have drawn this structure of a secondary halogenoalkane, and you can see that the alpha carbon, the one that is bonded to Cl, is on two sides there are carbon chains, and on one side there is a hydrogen atom attached. Now if you look at the structure of this molecule, you would notice that on one side the approach to this atom, this remember is a slight positive carbon atom, and this Cl is slight negative because of the polarized bond, Cl being highly electronegative. So on one side there are large groups attached around this carbon atom, so approach from this side is blocked, but from this other side there is hydrogen, and the approach from this side is not blocked. So if I have a nucleophile and an OH minus 1 nucleophile, let's pick the OH minus 1 nucleophile, then from this side, an attack from the opposite side, it would be attracted to this positive carbon atom, but the approach would be blocked because there are large groups. There are large groups like the CH3 chain and the CH3 chain over here. There are large groups on this side, so an approach from this side would be blocked. So an OH nucleophile would not be able to approach this carbon atom. But if it approaches at the right angle from this side, now there's a hydrogen atom attached, and that is not taking a lot of room, so it would be able to reach this particular carbon atom. So if it's able to reach this carbon atom, then Sn2 mechanism would be possible. This OH would approach this carbon atom, the Cl would leave this carbon atom, eventually the Cl would repel and would be knocked out, and the OH would take its place. But if the OH nucleophile is approaching from the other side, then there is no path available. There is no path available for an attack from the opposite side to get close to this positive carbon atom. So then an Sn1 mechanism would be more suitable. It's going to wait for the Cl to get knocked out, get polarized on its own, and a carbocation would be formed. And once a carbocation would be formed, then the OH could slip in and bond with this positive carbon atom. Now this entire step depends on a lot of things. So in simple words, a secondary halogenoalkane could have both Sn1 or Sn2 mechanism working for it. And a lot of times both mechanisms would be working simultaneously. If the OH is approaching from this side, then it has to wait for the Cl to break off. Only then will it get a room or a path available where it could attack this positive carbon atom. If it's approaching from this side, then this OH could directly go and bond with it, and the Cl could be knocked out like it's doing in this primary halogen or Sn2 mechanism. Now this depends on a lot of things. So I'm going to generally go over the conditions that might affect the mechanism. So if you're using a higher temperature, then there would be more chances. Higher temperature, or you're using a very polar solvent, then there would be a lot of chance of this Cl getting knocked out and this carbocation getting formed, because the possibility of the molecule getting polarized like the one in Sn1 mechanism would be very high. The chances of the Cl getting knocked out itself would be very high, and the formation of the carbocation would, the probability of the formation of carbocation would increase. So if you're using a very high temperature, or you're using a very polar solvent, then the formation of the carbocation would be easier, and this mechanism would start dominating. There are other conditions. For example, if you increase the concentration of OH ions, then if there's a very high concentration of OH ions, then they would be more likely to approach this carbon atom directly and attack this carbon atom directly, instead of approaching from the side where they are blocked. Increasing the concentration would increase the possibility of the OH approaching this carbon atom from the other side as well. Then there are other factors like the structure of the carbon chains. For example, you could have a highly branched carbon chain. If there's a highly branched carbon chain over here as well and over here as well, then it's going to block or cover this side as well, and it's going to block the entrance of this OH nucleophile from directly approaching this carbon atom. So it depends on a lot of things, whether Sn1 would dominate or Sn2 would dominate. It depends on the conditions, on the temperature, the type of solvent that's used, on the type of halogenalkanes, how branched are the carbon chains, and it also depends on the type of the nucleophile. Some nucleophiles are very strong, some nucleophiles are very weak. So if a nucleophile is very strong, then it's going to probably approach this positive carbon atom directly. The negative charge would have a very strong attraction for this positive carbon atom, and it would be approaching this carbon atom directly, like the one shown in Sn2 mechanism. So I've listed all the factors. What you just need to know is that for a secondary halogenoalkane, because they are in between a tertiary halogenoalkane and a primary halogenoalkane, both mechanisms could be possible simultaneously. One would generally dominate depending on the conditions, but you don't need to know that for A levels. What you just need to know is that both reaction mechanisms are possible for secondary halogenoalkanes.